Doppler effect was first described in 1842 by Austrian physicist Christian Doppler. Today it is used in astronomical measurements, in Mossbauer effect studies, in radar and modern navigation, in studying the motion of stars, and to search for double stars. It is also an integral part of modern theories of the universe. But what is it exactly? Perhaps it is best explained by an example. Imagine a bug in a pool of water. Every time the bug moves its arms and legs, it makes waves in the water. If it moves its legs and arms once every second, an observer standing a few feet away would see a wave come toward them every second. If the bug remains in the same spot and does not move, observers all around the puddle would also see waves coming toward them every second. But what if the bug were to start moving toward the right while still making movements with its arms and legs at the same frequency of once every second? Then, to an observer standing to the right of the puddle, the incoming waves would appear to be at a faster frequency than the waves approaching an observer standing to the left of the puddle. This is because the observer to the right is closer to the bug, and therefore the waves, than the observer to the left. This, in essence, describes the Doppler effect. Another way to explain it is with the example of an oncoming ambulance. When an ambulance approaches you, its siren has a higher pitch as it is approaching than when it is moving away. This is also because of the Doppler effect. It might seem simple and self-evident, but it is an important concept. In 1845, Dutch chemist and meteorologist Buys Ballot tested the hypothesis using sound waves. He found that a sound's pitch was higher than the emitted frequency when the sound source approached an observer, and lower than the emitted frequency when the sound source moved further away from the observer. This happens because the sound waves compress as they approach the observer. This increases the frequency of the wave, and the pitch rises. As the waves recede, the observer will hear a lower-pitched noise because the sound waves stretch out. This decreases the frequency of the wave, and the pitch falls. Meanwhile, French physicist Hippolyte Fizeau also stumbled independently on the same phenomenon in 1848. This has led to the French referring to the Doppler effect as the effet Doppler-Fizeau. Finally, also in 1848, Scottish civil engineer, naval architect, and shipbuilder John Scott Russell made an experimental study of the Doppler effect that proved Doppler's theory. Today, the Doppler effect even has applications in robotics. It is used in dynamic real-time path planning to help in the movement of robots, such as in robo-soccer. It can also be used in some types of radar to measure the velocity of detected objects, and in echocardiograms to generate an assessment of the speed and direction of blood flow. But where the theory finds perhaps its most prominent use is in astronomy. The Doppler effect is used to calculate the speed at which planets, stars, and galaxies are approaching or receding from us. It even helps us find and study new alien worlds. It seems the Doppler effect is a versatile concept indeed, with many useful applications. Can you think of another one?